So now we have Felipe Almeida-Fernandes, who's going to talk about the metallicity gradient of the Sagittarius Dwarf Spheroidal galaxy.
Okay, thank you. As I said, my name is Felipe Almeida-Fernandes. I'm a postdoc at the University of São Paulo. And today I'm going to talk about the metallicity gradient in the Sagittarius Dwarf Spheroidal galaxy. Actually, it's the metallicity gradient in the stream and how we use it to infer the original gradient of the progenitor. How do this work? Okay, so as Lais was mentioning, the galaxy has gone through some minor and major merger events. It's the hierarchical model of galaxy formation, so the Milky Way is no different. And there are some major events that are known in the Milky Way that we observe the remnants of these events in the halo of our galaxy, but my talk will focus on the Sagittarius stream, which is the most recent of these major events of merger of the Milky Way. And it's an ongoing event. So we have the core of the Sagittarius galaxy, the satellite galaxy that's being accreted by the Milky Way. But this interaction is producing this tidal, this stream from the tidal interaction between the galaxy and the satellite galaxy. So we have a trailing arm of stars and a leading arm of stars and a trailing arm of stars as well. And one important thing about Sagittarius is that it warps around the whole galaxy, so we can see this stream through the whole sky. There are two properties that are well known about Sagittarius. It is, at first, the metallicity distribution of the tails and of the arms and the core of the galaxy. And we see that the leading arm is more metal poor than the trailing arm. This is hard. Than the trailing arm. And also they are more metal poor than the core of the galaxy. So this is the metallicity distribution. And one thing that is important here is that this is from spectroscopic data, and only a few hundreds of stars were observed for this. And our goal is to improve, to increase the number of stars that we can use to measure this metallicity distribution. Another important property that is known is how this metallicity changes along the stream. So this is a coordinate system where the core of the galaxy is in the 0, and this is the coordinate along the Sagittarius stream. And what we see in the metallicity here on top is that there is a gradient in metallicity both for the trailing arm as well as for the leading arm. But again, I point out that there are very few stars here to measure this metallicity gradient, and our main goal is to increase the number of stars that we can use to measure these properties. And this is all done in the context of the SPLUS survey. It's been mentioned a lot in the conference already, but I'll give a quick introduction about SPLUS. So it is a southern photometric survey that's being done using the T80 South telescope. We plan to observe 9,000 square degrees in the southern hemisphere. It covers regions of high galactic latitude, represented in red here, as well as the anticenter of the galaxy and an area around the bulge, as well as the Magellanic clouds here in yellow. As I mentioned, we use the T80 South telescope, which is a small telescope, an 83-centimeter telescope located in Cerro Tololo in Chile. It is fully dedicated to SPLUS, except for the 10% of the time that is for Chilean institutes. And how can we use an 83-centimeter telescope to study things that are important that are relevant for the science that is done today? We can do it because SPLUS has this 12 filter system that includes 7 narrow bands. And these narrow bands are particularly sensitive to the metallicity of the stars. And just to mention, SPLUS is a large collaboration. I did a quick search about the papers that are being published using SPLUS data, and we have 48 entries in the ADS database, out of which around 30 are peer-reviewed papers. We have more than 100 members and more than 40 external collaborators, and we have meetings in Brazil as well as other countries. So SPLUS is not only a Brazilian community now, we are a South American collaboration. So about the photometric metallicities, what we did in SPLUS, we used an artificial neural network technique, and we trained it using data from Apogee and SDSS, and we are able to obtain photometric metallicities for the stars of SPLUS that we have the 12 filter information. And we applied this artificial neural network to the data release 4 of SPLUS, which is this area shown in blue here. So we don't cover the whole footprint of SPLUS yet, but as I'm going to show, we already can have some good results, even if with this limited area that has already been released. So the main results of the work for the Sagittarius stream, what we're doing, we're using this catalog from Ramos and collaborators 2022, which is this yellow dots here, and these are members of the Sagittarius stream. And what we did was cross-match the SPLUS data release 4 with the Ramos catalog, and then we did the coordinate transformation to get these stars in the coordinate system that is along the stream. So this is the core of the stream, this is the trailing arm of the stream, and this is the leading arm of the stream. And the first result we were able to reproduce, we did the metallicity distribution of the stream. And as we can see here, with many more stars than what we had with spectroscopic data, we are able to reproduce the difference between the metallicity distribution of the leading arm and the trailing arm. We can see that the leading arm is on average 0.2 dex in metallicity more metal poor than the trailing arm. And then we also measured the metallicity gradient, or tried to measure, because we see a very small metallicity gradient in the case of the trailing arm. And when we compared to the spectroscopic results here, the gradient was supposed to be bigger. But one thing that we did see is that if we limit the spectroscopic data to the same range of the SPLUS observations, we don't see a gradient, or we even see a negative gradient. But for the leading arm, the gradient is consistent with what we observe with the spectroscopy. And we have more stars with the photometry. And the next thing we did, we used any-body simulations from Vasiliev and collaborators. What they did was they use a spheroidal galaxy, and then they predicted the interaction of this with the Milky Way and taking into account the Large Magellanic Clouds, and they were able to reproduce the current state of the stream, starting from a dwarf spheroidal galaxy. But their study is basically a dynamical study. So what we did, we took the results from the simulation and we painted a metallicity gradient in the initial condition of the simulation, which is this dwarf spheroidal galaxy, and we follow the simulation to see how it produces the metallicity gradient that we see today. So this is the simulated data, and we can see that it predicts a very small gradient for the trailing arm, as we observe, and is also observed with spectroscopic data, and it predicts a larger gradient for the leading arm. And we did this for several different scenarios of initial metallicity gradient for the progenitor of Sagittarius. And we were able to constrain this original metallicity gradient from the current metallicity gradient that we measure for the stream. So this is our main result. On the y-axis, we have the current gradient in the stream, which is what we measure using SPLUS and using spectroscopic data as well. And on the x-axis, the different metallicity gradients that we imprinted on the initial step of the simulation. So we're able to constrain the possible values for this original metallicity gradient. And then we compared it to other satellite galaxies or other dwarf galaxies in the local universe. And the metallicity gradient that we measure is consistent with other metallicity gradients, although Sagittarius is more metal-rich in the core. But this is something that we observe with the spectroscopic data for the stars in the core of Sagittarius. So I'm already at take-home message. I think it was very quick. So the take-home message is that SPLUS is able to provide reliable photometric metallicities for hundreds of thousands of stars, and we were able to use it to predict the original metallicity gradient of the progenitor of the Sagittarius stream. And for the next steps, is basically we're going to publish this result, but as I mentioned, we did this for just the data release 4 of SPLUS, which covers a very limited area of the service. So we plan to revisit this in the future when we have more data and see if the results are the same. And also, I'd like to say that I'm looking for a postdoc, and this is my CV. So if you know about anything, please let me know. Thank you.
Thank you very much. Questions for Felipe?
Thank you, Felipe. That was great. And translating that to 3 languages, so much
thank
work.
you.
And making it fit.
Luis helped me with the Spanish. Thank you, Luis.
So, so this was very interesting. I wonder if you have data around the bifurcations of the 2 arms.
I don't think we have that data
Mm.
yet. Let me go back.
Because they're
maybe
very
here.
controversial. And
Yeah, but we can't see it here, but I think it's here.
yes.
But we don't have enough data in this region yet, but we will have data.
Okay.
So yeah. It's something we plan on
Yes, it
revisiting.
was more a curiosity then.
Yeah.
Maybe you mentioned it, or maybe it's a silly question, I don't know, but why going through the disk makes the gradient change? What is the physical reason for it?
I don't know exactly the physical reason for this, but
There's a hand there.
no, because it starts as a dwarf spheroidal galaxy, and
Yeah.
these stars are going to be taken away from this. But the stars that are on the outskirts of this will be ripped out earlier.
Michael
So-
has the answer.
Yeah, maybe he has the answer.
Okay.
Of course, you strip the outside star. You strip the outside stars first, and then further and further inwards. So now you have tails to both sides, and at the end there are the outermost stars, and closer to the core are the more inward stars. Now the length of the tails depends on which position of the orbit is Sagittarius. The tidal tails of any object, if we are close to the apocenter of the orbit, the tails shrink and come together because the stars get slower and slower and slower on their orbit. That's Kepler. We are slower further away from the sun. We are faster, closer to a planet is faster, closer to the sun. Same thing with the stars in the tidal tails. So close to apocenter, the tails shrink together and come closer to the object. And once they are close to pericenter, they speed up. So first the leading arm stars speed up and stretch out. Then the object gets faster. Then the trailing arm speeds up and stretches out. So it might be that the leading arm is already stretched out. The trailing arm is still on the way to get past pericenter and get stretched out again. And once the whole thing gets back to apocenter, they come together.
I think this probably explains why we see it different in the gradient in each arm. So yeah.
Nice presentation, Felipe. Thanks.
Thanks.
I saw a work, I guess, a month ago in IAG that talked about it compared SPLUS data with WISE data, I guess, and found some kind of offset in the U band. Do you know something about this?
Was it the work of Guilherme Bolutavicio?
Yes.
Oh, he's my undergrad student.
Yeah.
Okay. What we did basically was we were trying to reproduce the SDSS magnitudes using SPLUS, and then he saw that adding 0.04 in the U band improves the result. But this is something that we're still working on to try to understand where this is coming from.
Bruno.
Hi, Felipe. Nice talk.
Hello.
So I was wondering about the metallicities. So which bands do you use for the metallicity and which precision you get for individual stars, or how do you beam them? Things like that.
Yeah, the precision actually depends on the metallicity range because we're going down to -3, but when we get 2 metal poor, the uncertainty increases. But for the filters, we're using all of them in this case because this is a neural network, so it receives all the filters of SPLUS as an input. But one work that's being done is seeing which filters are more important when predicting these stellar parameters. But for now, we're using all the 12 filters.
I call Debasish, and then thank you very much. Now Debasish Hazarika will talk about unveiling galactic secrets, chemical tagging of Milky Way variable stars with SPLUS.
Hello. Yeah, thank you, Dante. My name is Debasish. I'm a PhD student at the University of Atacama. So I'll be talking about chemical tagging of Milky Way variable stars using SPLUS. So it's a similar kind of things that my previous speaker has already presented. So basically, as it was mentioned many a times that when we talk about lambda CDM cosmology, that says that larger structures are the results of some mergers. So to decode that past, we need to think more about like kinematics, dynamics, and chemical abundances to decode the history. So in that case, in merger events, in some cases, the dynamics is lost, but the stellar atmospheric chemical abundances remains intact. So that could be a one important clue for looking at the history. So as you can see here, we want one work recently published, which are like describing the complex scenario of the past merger events using various kind of probes. So that is the things. So now why we are interested in variable stars as a probe in that scenario? Because we have a wide range of variable stars spanning in the instability trees, instability strip. We can see here. Yeah. So when we go from very short period variables to long period variables, these are also distributed throughout the whole galaxy, and mostly like RRLA-LARIMs, which are like ideal for the halo properties because those are all metal poor stars. Similarly, we have in the lower like the delta scutis, which are very, very short period variables. So when we talk about the studying the abundances, we need to go for the spectroscopy. But to study the spectroscopy for this type of short period variables is really very challenging, because when we go for the high resolution spectroscopy, the short period becomes smaller than the exposure time for that. So it creates some problems. So the estimations for the short period variables becomes complex in these cases. So basically we have a like trade-off between the high resolution and short-term pulsations. That is one cause. And another one is that to determine the center of mass radial velocity for this type of short period variables is really challenging, because it requires some pulsation models to disentangle the effect of pulsation while observing the spectrums. So this type of challenges actually encourages us to look for some alternative approach to look for those abundances. So with that motivation, like our aim is to determine the chemical abundances of variable stars basically in these abundance spaces using the SPLUS, and also to position them within the Milky Way components. So basically, as Felipe has already mentioned, like he has well described about the SPLUS, it has like a 5 SDSS like wide band filters and 7 narrow band filters, which are like specially designed for these lines. So we are using the single epoch data from DR4. So for the variable stars in 12 magnitude bands, so which can be corresponds to like 66 color combinations, and 10 that were fed to some machine learning models based on some available spectroscopic informations. So initially, when we do the cross matching, considering few astrometric cutoffs, as well as some removing some contaminations, contaminated stars from the sources, from the backgrounds. So we came up with around 35,000 plus variable stars from the PSX and Gaia data release tree. But interestingly, here there's a one region, like one class, which are like not well classified. So we termed it as a variable stars only. So which actually bears the major roles. And then comes about the known variables. Here we have some eclipsing binary candidates, and also the RRLA-LARIM and the classical CFITs. So with that, like we utilized three spectroscopic surveys for the known objects, using the Lamos medium resolution and APOSI high resolution and Gala high resolution data release tree. But interestingly, for Lamet and APOSI, the predicted abundances were not so satisfactory with when we compare with the known values. But for the Gala, it shows some prominent things, and we have fed this with an random forest regressor, considering some parameter grids for the hyperparameter tuning. And we considered some criteria described by this author, Chan, to adjust the sample distributions, because in our case, as we have seen in the previous cases, the data were unbalanced. And finally, based on that, from the predicted values, we considered the values which have like a prediction confidence score like more than 90%. So with that, we see that this is showing like for the predicted versus true values for the iron, for the metallicity as well as alpha elements, it shows promising in this case. And as Felipe has mentioned that for the lower metallicities, yes, that's the errors are like more. So this is the distribution of the predicted chemical abundances. As we can see here, the metallicity basically ranges is like a
are more important for each of the abundances, or is it possible to do that?
Not exactly, but we try to some combinations. For example, in this case, like we are using 66 colors derived from the 12 magnitude bands. But when we gradually decrease the numbers, then the error increases. Like, so that is the case. But that is, well, that's a good question, like to which color is contributing more. Initially, we thought that we will be considering the extremes to like from this like U band and like Z bands, and considering the two colors from like U minus Z or Z minus U, that we were thinking that maybe it will work, but it does not work that way. So recently there are some papers also I was studying, and that also says that there are some non-linear complex correlation between the colors and the abundance spaces. So it is quite complex, I think, directly to say that whether it is which color is contributing more. But well, I have that in my mind.
Okay, thank you.
More questions? Yes.
Do you also estimate other parameters of the stars when you estimate the abundances, like temperature and surface gravity?
Actually, mostly for our samples, like 35,000 these stars, mostly the effective temperature and log Z values we got mostly in the APOSI, Lamos, and Gala databases.
Okay, so those are fixed.
Yeah, so we are not doing, but if we have very limited number of abundances, because these are the variable stars, as I have mentioned. That's why probably the spectroscopy were not done yet fully. Yeah.
Yeah. Okay.
I just realized you talked about temperature and gravity from other surveys.
Yes.
Is this an input for your code to fit the abundances, or you don't need them at all?
Actually, we at one moment we are trying to put effective temperature, but there were some issues because of the higher values, like it seems like it is taking all the hyperparameters towards, is it dragging all the hyperparameters towards them, because all the other cases like the elemental abundances, which are like fractions, but that becomes like a big thing. So we are still trying to incorporate that one, but till now we have not yet.
So you don't use temperature and
Yeah,
gravity
it
to
have
determine that?
Have not done yet, but
Okay.
we will look into that. Yeah.
Okay, thank you.
Last question.
Hi, Debasish. That was great. Yes. Okay, so I have a question. I'm not sure if you already answered it because I may have got lost a bit. But I wonder what the coverage of the alpha to iron and iron to H to just iron to hydrogen plane is of your comparison sample, because sometimes it would be, you would think, I really don't want to be mean, you would think that because alpha and iron are very correlated, if you're looking just at halo and thick disk stars, you might be recovering alpha because you're recovering iron, but not because you're recovering alpha itself. So have you considered maybe, or checked that you have things that have the same iron but different alpha in your comparison sample?
Not yet directly like that, but only with we have compared with very limited number of RRLA stars with we have the photometric light curves. So that's only, but it's very limited in number, like 13 or thing like that.
Yes,
but we have not seen that way, so we will look into that.
Yes, I'm asking maybe even with other stars, not RLA, because there are so few that have alpha from. That's such hard work, and this would be enormous contributions. So yes, okay, we'll talk more.
Yeah.
Yeah, I think the T&E groups will take care of that when you do the groups classification for the different elements. But one quick last question: what fraction of your stars are counter-rotating of this group of 27?
I think
is it?
Yeah, we have done it.
1/3. Okay.
Yeah, it's very few like this. Yeah.
Thank you very much. See, if we show enthusiasm, all the speakers keep to the time assigned, like Francesco Mauro, our next speaker, will do. He is going to talk about an internal view of the stellar system Terzan 5.
Okay. Nice to be here. Also, thanks to the SOC for choosing me for a talk. We are trying to finish for several years about the GSOI data in Terzan 5. No. A stellar system, not a globular cluster. Please don't call these things a globular cluster. The outline, simply we are presenting Terzan 5. What is Terzan size? Also, why we are looking at it, the new data from GenSOI, new catalog, and some preliminary analysis. Terzan 5, who's who? Became famous in 2009 with Ferraro that observing in infrared discovered the famous double horizontal branch. Not only this, but to fit this to double horizontal branch, you need quite different isochron. One of 12 gigayears and the other of 6 gigayears. Now seems 5. It's this system slept for 6-7 gigayears before restarting a new population, and with a nice difference also in metallicity, because from -0.2 to +0.3. The two populations show quite a different distribution, not so in the original data, not so similar. not different, quite similar from the field. I say that you need a quite different isochrone to fit the data, and we can see the two populations are quite different, where the young, as expected, they should be more concentrated in the side. Finally, in 2017, we got the data after 3 years of asking, rejecting, applying again, getting time, bad weather. In 2015, 2016, this is the famous, there was a lot of rain, it was JSOI almost doesn't observe. Finally, we get the data and are quite nice and quite complicated. You can see this is in the center, there are really a lot of stars. You can, and these things is thought to have 1 million stars, 1 million solar masses, so it's really huge. And the pixel scale is 20 millisecond, while Vista for the VVV has 340 millisecond per pixel. So you can, what is previously 1 pixel, now it's allowed 17. Obviously, everything elaborated with my pipeline. I needed to mention it at least once. The calibration, we did everything, tried to match. The calibration was quite how to calibrate exactly, because first fit with the dependence of color, there is a little dependence. Then I try fit with simply a constant. Could be possible because Vista and Gemini are thought to observe in visible and infrared. Could be a similar, just an offset between them. I definitely go for the constant simply because the RMS of the fit are really, really small. Was changing a factor of at 100, 1000. So if you increase the fit, the degree of the fit, you have a little small in the chi-square. Probably is not correct to increase the fit. The matching between VV JSY was quite good, and obviously you can see here problematic. If you start with a little small distance, everything okay. Just to a reference, the VVV astrometrics is not so worse than Gaia. You can have it's like Gaia in less than 1/10 of a second. If you increase it, you increase the stars fitted, but you want to have some difference. The reason is also because, as I said, JSOI data, it's a really nice instrument. I love it. I work for the commissioning, but has drastically too many stars. When you start to match, you can have where an instrument see 1 star, JSY see 10, 5 stars there. So it's definitely problematic to do the match because usually you have, for example, difference of 3 magnitude between the 2 stars, maybe because it's a wrong match or because there was not 1 star, was several. But okay, we did it. The improvement between VVV JSY, you can see this is VVV in J, in K. In K, the error is not so big simply because VVV you can have up to 80 epochs, so you can increase the precision of your measurement as you want. This is partially with just a part of VVV, but we now have essentially, except for this area that was really bright stars, we can have a really nice cover of the area inside it. just is not really noticeable, but here the chip 4, it's a little less detected stars, probably in the faintest, so will be not much problem. But for at least here are 5 arc minutes of area. This is the total in this case of the CMD, and where is the 2 horizontal branch. So doing as before, we select the 2 horizontal branch and do some calculation to check for the frequency, the distribution from the center, and it's here you seems not so different, but you can see there are in the brightest, that is also the youngest, it seemed at the beginning to be a little more than dropped, while the green part are the faintest, it is also the oldest. Checking, okay, here in logarithmic scale, you can see a little better that in the inner part, that was the original data was just up here, like the 0.7 arc minutes. You have the outside more of the oldest stars, less on the youngest. The youngest tend to increase in the inner part. Then it seems to stop. It's not that peak should be there, but definitely you can see there is outside there is more of the faintest stars that are the oldest. Here is you can see the red line is that is the brightest horizontal branch. In looking at the cumulative, you can see like a little better like difference, because the brightest, that is the youngest, try to are definitely you can see it is more concentrated, because increase more rapidly, then stay quite still, while the faintest are definitely little difference from before the previous cumulative distribution, but this usually they stopped at 0.7. Now merging GSOI plus VVV, you can go as far as we want. Now we just check at 2 arc minus and half. It's like increasing, still increasing up to the end, so it's not quite going flat. And here, just to comparison, the difference in the cumulative, the difference and the ratio from the 2, so definitely it are not the same distribution. Future step. We have also some HST photometry in V and I that we will put together. Essentially not now, because we just want to see the horizontal branch, but since we want to do the reddening, we need, it's better to have some bigger doing with the I and the K short. That will be quite problematic, because usually do the rendering with the diffusion line, you move the stars along the rendering line. In this case, you have 2 diffusion lines. So you have also to understand which value is correct. Should be that for each area, each stars gives you 2 votes for the value, and then you check for the highest, the more voted value. Also do a little more cleaning increase the area, and then so we can do a nice analysis of the also the horizontal branch, but mainly on the turn-off and the subgiant branch to see exactly if there are just two population or there is something more. Thank you.
Thank you very much, Francesco. Questions? Yes, please.
Thank you. Really nice talk. Terzan 5 is a really interesting object. I'm very interested on the plus 30 millisecond pulsar that it has. So I have a question with this instrument. Can you do any sort of variability? Is it possible? Because you show that maybe the magnitude changes. And
Variability, something really fast, okay, because asking for GSY is not so easy. They need just in the top quality of the sky in a band. So it's quite competitive, especially for the supernova guy. They are asking time as crazy. So you can do maybe better with SOAR, that you can have a little more time, because GSOI can be quite problematic to have several epochs and also get several epochs. If you need something really in the center, maybe you can give them the motivation to get the time.
And can you do also narrow bands? Some sort of
GSOI have everything.
What?
GSOI have 16 filters. In the near infrared, there's a broadband, narrow band, a lot.
And how many filters do you have for this?
In this was just 2, because we are more interested in K short, but the J was for calibration, but anyway are quite good, so we can add it and it's not complete as a VVV that are Z, Y, J, H, K, but at least we have both J and K short.
More questions for Francesco? Yes, Javier, in the back.
Hi, Francesco. Very nice talk. So, how many of the globular clusters of the Milky Way are you expecting to be not globular clusters, but these nice stellar systems? So, like Terzan 5.
We have 3 at least. The Omega Centauri, then there are Terzan 5 and Linear 1. They are well known. They are building blocks and not a globular cluster. Other, they are like these 2 crazy guys. I don't remember them so much. But that should not be so much, because it should be the building blocks of the bulge. So the system that was originally 100 million, 1 giga elements that was given to the bulge. The bulge is quite big, so probably there are just these 2 that are still alive. The other completely, or just the inner part seems really like a globular cluster, because all the population is away.
Okay, thank you.
I guess, I mean, I do global cluster, but for compact binaries, I never color stellar system, but we use them to calibrate these X-rays and how many X-ray binaries. So should we be taking these apart, Terzan 5, Omega Cent, as just, because again, this one is weird, bunch of millisecond pulsars. Is that why? Because it's a weird stellar system, not a global cluster?
It's Terzan 5, I say, the Terzan 5 and Linear 1 are thought to be the building blocks of the bulge. So was not something small created in the product of the Milky Way, but produced during formation or coming outside. So it's a small, a big system like in the Selezin way or Lambda CM way. Depends. Selezin is produced during the collapse of the the gas or produce outside and enter to giving away their stars to produce the bulge. That makes sense because if you start with 1 billion stars, you can produce this lot of pulsars that is famous Terzan 5, that is essentially, and also Linear 1 seems to quite similar. Linear 1 is even stranger because the second population is 1-2 gigahertz. So yesterday, essentially. And yeah, it's are strange guys, but unluckily, I don't hope that we can find the other ones because they're just leftovers.
Okay, thank you very much, Francesco. And also all the speakers, very interesting talks, and thank you for sticking to the time. And thanks to the organizers, and we are done.